Welcome, everybody. It's my pleasure today to announce that Kevin Jamieson will be giving a talk in our online learning, in our online reading group. So Kevin is a very established researcher at the University of Washington. He did previously studied at the University of Wisconsin, then moved to Columbia for his master's, and then moved to Washington to University of Wisconsin to work with Rob Novak. And after a postdoc with Ben Recht in California, he joined as a faculty at the University of Washington. He did amazing work in sequential decision making, and especially in instance optimal algorithms, which I think is a very impressive work. And without further ado, thank you for speaking.
Thank you. Thank you so much for the invitation. Probably most of you know, but this group has been hosting a great series of workshops at conferences in active learning. I was invited to speak very generously at SCML, but I came down with COVID and couldn't speak at the last minute. So it was kind of a tragedy. So I was so happy to be able to have this opportunity today. So today, this is kind of an unusual talk for me. Usually I'm more used to talking about, algorithm development and analysis, and most of the time, the stuff that's going to appear in this talk about, deploying it in the wild, usually only ends up being on like one or two slides in the whole sort of talk. And it's like, oh, and we actually implemented it. We got it to work. And it's just funny because, that is a small amount of what my research time is, but when I do work with companies, a vast majority of my time is spent more on sort of like the nitty gritty, like details and issues that come up that my published research doesn't really address completely. So I like that I had this opportunity to talk about it. But that also means that I'm not in good practice of giving this kind of talk. So I'd really encourage you to interrupt me, ask questions, and if this was more of an interactive environment, and talking about, hey, what did you actually do here, or what are problems, what's your experience with this? I'd really welcome that. So let's dive in. So I've really been getting into experimental design, and over the last 5 years or so, I've really gone back to the early sort of sources on experimental design and trying to kind of trace its history. And it's been a very sort of interesting pursuit, because as you look back at that earlier sort of literature, they were trying to solve problems where they had very, very few samples, like on the order of tens. And they were trying to just eke out as much as they could. And it was a very applied sort of science, and not like super rigorous. The confidence intervals were, you don't really trust them. But, as modern technologies have really amped up the ability to have large sample sizes, people are willing to and want to, try to go after small effect sizes, and just have, just enormous amounts of samples through automation. And it's really sort of pushed us into weird sort of areas where the assumptions that would break down in these small sample sizes, we didn't really care too much about it. But when the assumptions start breaking down, when we're getting tens of thousands or even millions of samples, we really start to notice. And we have to be a lot more careful about what we're actually selling and talking about. Just so everyone's on the same page, this talk is about interactive learning or active learning or adaptive experimental design. I use these terms interchangeably and synonymously, but let's just get on the same page here. So the way I think of experimental design or adaptive experimental design is that you start with some goal metric, like you want to learn a classifier or a contextual bandit policy or something like this. And you also consider a bunch of probabilistic models. How is the world interacting with your data and with your model? And then given these sort of goal metric and probabilistic models, you're going to take a look at what experiments you can make, and you're going to choose ones that are going to give you the most information. And once you decide what measurements you're going to take, you go and interact with that environment, observe your outcomes. And then the adaptive part is that you go and actually update your set of hypotheses or probabilistic models and repeat this closed loop. And that's what we try to do here. And the hope is that you can try to reduce the sample complexity, the total number of interactions with that environment before the goal metric is met in some way. And so my research has been, as alluded to, really has tried to emphasize going beyond worst case or beyond minimax and going after instance-dependent results, so that if the problem is easy, then you require fewer samples. If it's hard, then you require more samples, but your algorithm will adapt to the sort of the true difficulty of the problem. I have really focused on pure exploration, and that is in contrast to focusing on regret minimization. And I think I'm kind of excited about this talk because it gives me an opportunity to explain why. I'm kind of somewhat of an outlier, that like the vast majority of my work is on pure exploration. And hopefully by the end of this talk, you'll understand why I do that and why I care about those problems. And so in the interactive learning problems that I look at, they all sort of look the same. You choose some measurement or policy in some space, you observe some true function plus noise, and maybe you want to do optimization. You want to find some X that maximizes some property, because it could be binding affinity with peptides or hyperparameter tuning, trying to find some hyperparameters. Did a little bit of that work. Or it could be estimation. I just want to learn the function. I know something about it, and how do I strategically take measurements in order to lock down what the true function is? Or it could be more sort of a classical active learning for classification, where I'm trying to identify like big sets of things. This could be identifying like level sets of functions, or a really tangible sort of example is in the space of antibiotics. If we're looking for combinations of antibiotics that sort of kill or successfully accomplish some goal, I want to identify sort of all of the combinations that are above some threshold. And so that's a classification type task. And then also more recently, I've been getting a lot more into reinforcement learning. Very exciting math. It's very, very fun. A lot of open problems there. And I'm looking at different models there. But I'm not going to be talking about that today. So as alluded to before in the last slide, a couple slides ago, there are sort of traditional methods, a fixed experimental design or a random sampling design. We expect, if you're doing say classification, the error to go down at some rate. But if you're doing it adaptively, basically deciding what sample to take based on all the previous measurements you've observed, then you might expect the error to decrease a lot faster. And what this talk is really about is somewhat focusing on the idea that it's actually a huge amount more effort to deploy adaptive sampling than random sampling. And like all these nightmares that come up, we don't really talk about in our research papers, but they really are going to be the majority of your time when actually going to a company working or doing something in science. And like the kind of issues that come up are that you need to worry a lot more about latency and computation. If you go to a small startup or something, 99.9% of your time is going to be spent talking about infrastructure and systems. Most companies don't start their company thinking that they're going to be running lots of A/B tests and adaptive experimentation. And so the way that they've set up their systems is not easily amenable to that. And you'll spend a lot of time just working on the plumbing to get A/B testing just running. And related to this is getting reliable logging. If you're doing adaptive data collection, now you have a biased data set almost by design, and that can lead to other downstream issues. Hardware is constantly changing, software is changing. In the worst case, you can get terrible feedback loops and Simpson's paradox type issues. And a lot of time when you actually go work for companies and you're trying to convince them to do something adaptive, or they know they want to do something adaptive, before they let you implement it, there's going to be a ton of your time dedicated to education, explaining what the algorithm is doing and what the sort of pitfalls are and what you have to be very careful of, because they know that when you leave, they have to run this thing. So there's all these issues when you try to deploy active learning or bandit algorithms in the wild. Um, and very little of that time when you're actually doing that is talking or thinking about algorithm analysis, which is the vast majority of what my actual research in my day job is, working with students in the university setting. And it's the things I think about. But there's a lot of interplay between my research, doing the theoretical analyses and the models I consider, and working with industry. And so even though there's all these nightmares and challenges, I do strongly recommend working with industry as much as possible to understand what the real challenges there are, and how to just basically generate problem statements. So in my little bio that was just given, I did my PhD at Wisconsin, and up until about 2017 during my postdoc, I was interested in a lot of things. Started with making a beer app that was released on the App Store and got a lot of users with like pairwise comparison type feature stuff. I looked on derivative optimization and working with like MEG data. That was a nightmare. Didn't really work. And I worked a lot with psychologists. So here in this sort of application, they wanted to find embeddings of sort of words, emotional words. And when you'd ask people questions like, is fear closer to joy or sadness? And this is sort of the first lesson I had in like that you really need to be taking systems seriously, and you need to learn how to run a system. And around this time, I got very lucky and got hooked up with New Yorker magazine, and to run sort of a caption contest for them using adaptive algorithms. And that was a really great opportunity I'll talk a little bit more about in a second. But during this, I'm really trying to emphasize that to actually deploy active learning, what I realized later in my PhD was that you really needed a system. You need to be a systems engineer. And so I built this thing called Next to try to make it a lot easier to deploy active learning. And it was very relevant at the time, I felt. But it turned out that, just a few short years later, Amazon Web Services just became so spectacularly good and made it so easy that it's less necessary today. And so after 2017, so once I joined faculty, I started working a lot closer with industry, trying to embed myself within companies, mostly because I could avoid those systems issues and work with engineers that are really, really good at systems, and I could just focus on the algorithm design. And so a lot of this work was in online experimentation, so adaptive A/B testing, multi-time bandits, working with companies like Optimizely, Amazon, and Kiva. But it also led to more contextual bandit style algorithms and applications. At Amazon, I work in Amazon robotics. And so I've had a lot of different experiences there. And then also I have some experiences with the sciences. I can talk more about that later. That's not what this talk is about. That's still on the level of like 10,000s of measurements, not millions. But that comes with a whole host of challenges that if you're interested, you can ask me at the end. So the plan for today is to talk about these three experiences that I've had mostly in real-time bandits, online experimentation, and contextual bandits. So that's the plan today. What I'm going to do in the first part of the talk, when I'm talking about this multi-time bandit stuff, I'm going to essentially mirror what I would do if I was giving a tech talk, a talk on my typical research, and then I'm going to kind of scratch the record or stop and tell you what did we actually do in practice. Instead of just saying, oh, we went and implemented it, I'm going to talk a little bit more about what actually got implemented and what were the issues that come up when you try to implement state-of-the-art research. And then I'll do the same for the contextual bandits. So let's start with the New York capture contest. So the New Yorker magazine, in the back of the magazine, they have a cartoon, and they post a cartoon every week, and they encourage people to submit captions. And so for this particular contest is a long time ago. Again, this particular work is quite old. but it's still relevant to our discussion here. This is the third place winner, maybe a second week will go better. Oh, for context, Trump had just been gone into office. I'd like to see other people. The corrupt media will blow this way out of proportion. And so, but of these three, how were they selected? So Bob Mankoff, the former editor at New Yorker, cartoon editor, he would actually look at these captions that were all submitted and then choose a short list that would then be cut down even more by other staff, and then they would pick three that would then be voted upon by people. But he had this vision to try to do this, to crowdsource the entire contest. So they get about 5,000 captions each week. And what they wanted to do was invite their readers to a website and actually just start rating these captions and to try to crowdsource the entire process. And so it's getting people more involved, and it has the side benefit of him not having to look at 5,000 captions each week. But the goal is to identify the finest caption. So this is what it looks like. You're showing some cartoon, so showing some caption. So it's a boardroom with a plant on the edge of the table. It's amazing to think he started out in the lobby. Unfunny or funny. I thought all our plants moved to Mexico. Unfunny or funny. Be patient, he'll grow on you. Unfunny or funny. And so every time you press unfunny or funny, it's showing some new caption, and it's asking whether you like it or not. And the idea here was you could just treat this as an A/B testing problem and just do a completely not uniform, non-adaptive, show one of the 5,000 uniform ran. But immediately, the vast majority of these captions are really bad. People are not that clever on average, is my understanding, or what I kind of understand. And most of them are just terrible. And very quickly, you can stop showing the bad captions and hone in on the top, say, few hundred that are actually funny and worth looking at. And so an adaptive strategy would figure out what those top 100 are and just sort of focus all the attention on those and stop showing the ones that really have no chance of winning. So this was the goal. And I always like put this plot up here saying that yeah, we win. So with the adaptive algorithm I'm about to talk about, we could actually show that we're getting about 4 to 5 times speed up over non-adaptive. Because like I said, the vast majority of these are really bad, and it becomes very obvious that they're bad in the beginning. So this has been going on for 300 weeks. Like I said, this work started in my PhD a long time ago. And we get about 750,000 votes a week, so almost 1 million, and about 40,000 unique visitors. Well, Jane, my close colleague at UW, we also were at Wisconsin together. He was instrumental in also getting this to work, and still really helps out with it a lot more than I do.
So we have a quick question by Johannes, I think.
Yeah, shoot.
You need to unmute yourself, please.
Johannes, we can't hear you. Seems like we've got some technical issues. Johannes, when you resolved it, maybe we can, at the end of this section, I can.
Okay, Johannes, maybe you can type in the question and then we'll ask at some point.
Okay. All right, yeah, let's return to that later. Okay, so the idea here is, as modeling this as a Bandit problem, user relies the platform, algorithm chooses a caption 1 to n, and then the user votes funny or unfunny with some probability mu I. And so then the objective here is to identify the argmax mu I using as few total samples as possible. Okay. This is a model that will fail in many ways, as we'll discuss in a moment. But the idea, if I was giving sort of an algorithms talk, the idea here is that after I get some number of votes of funny from each person, from a lot of people, I have, since it's a finite amount, I have some confidence intervals on what the sort of the true funniness is of each caption. These confidence intervals are shown in red here. And these confidence intervals go down like root log n over number of votes, where n is the number of captions. And the idea is the more votes we get, the smaller the confidence intervals, and eventually we'll keep sampling until the confidence intervals don't overlap, and then we can confidently decide that this is the best caption because its confidence interval is strictly above all the other captions. And this would happen if we did it uniformly. So these confidence intervals are all the same width because I kind of simulated if doing all the showing all the captions the same number of times. And if doing a little, if we call delta 2 the gap between the best caption and the second best, delta 3 best caption and the third best, it's just mu1 minus mu3, then it's really easy to just sort of set this gap equal to this confidence interval and observe that if you're doing non-adaptive, you're going to have to wait for the smallest gap to be overcome, the variance of the smallest gap to be overcome, and with the same complexity. But it's very weak because you did not put samples on these ones down here, or you put too many samples on these ones down here, these very bad ones. Really, you just see these confidence intervals be less than this blue line, but you ask way more samples, and so its confidence intervals way smaller, and you wasted time. And so a slightly less naive thing to do is to just, as soon as you keep sampling, and at the first time that you can say that this caption definitely cannot win because its confidence is strictly below any other caption's confidence interval, stop sampling it. So this is the idea of successful elimination, and you get a sample complexity that's like delta I minus 2 log n. Okay. So this is the difference between sort of the successive elimination approach and the non-adaptive approach. You can think of this as like n times the max, which is like n times the average inverse gap. And so you can play around with the gaps to see when you start to get a win over this sort of strategy. I got fascinated in this problem because the lower bound was this delta I minus 2 bound. And so the upper bound and lower bound were off by a factor of log n. And this really happens because this log n explicitly appears in the confidence interval because the confidence interval, you have to have this union bound. And so if you have lots of captions, this can be significant. So I came up with an algorithm based on the popular UCB algorithm. But basically, instead of having a log n here to union bound over the different captions, I just sort of defined this thing. It's not a confidence interval. It is not guaranteed that the empirical means are inside these intervals. But nevertheless, I still sort of play the algorithm. And you can show that eventually, if you do this procedure, there's some stopping time in the future at which the best caption will poke its head above all the other ones. You can define some stopping time, and you can eventually show that that stopping time is just the sum of the inverse gap squared without the log n. Okay, so that's sort of like the theoretical story. And then I would, in a typical talk, I would talk more about the theory and maybe about how we extended this result. And then I'd show a slide. I'm like, yeah, we did it. And like, it worked. But now I want to show you one more example on the web of experimentation. And then I'll tell you how we actually did it. But before going on to the next example, are there any questions? My question is on the plot comparing adaptive and non-adaptive. Yeah. What's the ground truth best caption here? Not sure why you can't hear me. I was on mute. Okay, great question. So what we do for these kinds of plots, whoa, that was weird. In the back. Great question. So what we do here is this was given some number of queries. And then what we would do is we would do a non-adaptive test of both of these algorithms. And then just show that to many, many, many people. So, okay, so said again, the way, yeah, that's actually a good point. So one way to actually benchmark different algorithms, if you have 3 different adaptive algorithms and 1 non-adaptive algorithm, the way to benchmark these things in a system like this, one way is to you A/B test all the say 4 or 5 algorithms, whatever there is, And so at each time when someone shows up, you uniformly at random draw an algorithm and then use that algorithm to tell which caption to take. And they all use their own data separately. They don't share data in any way. And so then at the end of some period, each algorithm, each of the 5 algorithms, let's say, will have their own estimate of what is the best caption. Okay, they'll have their own list of like what they think is the best. And so then we'll take sort of like the top 100 of each algorithm, and then we will start a new sort of A/B test where we just take the union of the 100 from each of the 5 algorithms. So this could be at most 500, but it's typically more like let's say 200 because there's a lot of overlap. And then among those, the union of all the lists, we just do non-adaptive over those, and we get many looks and many clicks on those. And so we get a very, very accurate look at what how that reduced set is rated. And the reason why we do this is because if we just showed all 5,000 uniformly at random, we wouldn't get that nice statistical significance that we'd want. We wouldn't get that clear ordering. But by doing it this way, by having each algorithm play separately, output some list of say their top 100, and then take the union of all those lists, and then do a very exhaustive sort of study on those, we can get an idea of what the best one was. And this is a strategy that we use a lot when benchmarking adaptive algorithms. Okay, I hope that answers your question. Okay, so this is the Bandit sort of story. And now I want to move into online experimentation. So when I first started as faculty, I was approached by Optimizely. Optimizely is the biggest A/B testing platform or experimentation platform on the web, just in terms of numbers. So like they do all sorts of customers like New York Times, Hertz, Blue Apron, eBay, Microsoft, ASICS, et cetera, et cetera. And basically, what's New York Times doing with them? They're A/B testing headlines or experiences or ad campaigns, sort of things of like not so much the ads themselves, but like where do they put them? How do they insert them into the articles? That kind of thing. And if you don't know what Optimizely is, if you look at big websites, they almost all have an Optimizely little snippet because they're just so frequently used. It's amazing. It's the biggest website you've never heard of. And so the goal, what they had, why I was there, is they would often have sort of many variations of a website, and they'd have some control. The control is like what's currently deployed. And they want to find all those variations that are at least as good or better than the control. Okay. And so it's kind of a level set problem. You can think about it. It's saying, and it's A/B testing, but it's not saying I want to find the best. It's saying I have all these variations, which ones are better than the control? Because then what you could do is then take that information, what were the best, try to figure out what was common in them, and then make decisions based on that. The problem is that you can easily generate many variations on the website, and through sort of a combinatorial explosion of opportunities. And so they want this adaptively, because if you do it passively, there's just a lot of experiments that can be run. So this was a very interesting problem, because at the time I was actually already starting to think about this, but more from the context of genes, of RNAi. So RNAi is an older technology that's not used anymore. Now we use CRISPR. But the idea here was that you would inhibit some gene, measure some fluorescence, and if that gene was really important to this process, and you knocked it out, then this would get a lot of fluorescence versus a small fluorescence if that gene didn't really matter. Basic science. Now, so what you would measure this is like if you look at the ith arm or ith gene, you'd observe some Gaussian random variable with some μi, where a larger value of μi means it's more significant. And if you measure this multiple times, then of course you get the same mean, but you have this variance decrease like 1 over k. And the objective is to output some set S where if you have, there's no effect, or it could be a negative, less than or equal to 0, or a positive effect. And you're trying to find all those genes or website designs that have some positive effect. So you want to output some set S that has high intersection with H1 and low intersection with S. So just like with the captions, if you take some number of measurements, you're going to have some confidence intervals. And to solve this problem, as you keep measuring each one, confidence will shrink. And then after a while, some will still be overlapping 0, meaning we can't rule them out as being the null hypothesis, being mean 0. But some will have positive means, and we can then discard those, or say like these ones are actually the good ones.
So Kevin, just a quick question. So in both of these applications, how do you sub-select the arms, right? Like, because you have like a combinatorial number of them, right?
Yeah.
So how do you select the set that you work with?
So we assume that they give us some n variations that they like. So this could be this could be like 5, it could be like 50. And so we assume that they give them to us. But then when we run this procedure and we're adaptively sampling, we're trying to figure out which ones are the good ones, which ones are the worthless ones. And then how we actually, once given any number of measurements, given any number of sort of after measuring all these genes or variations some number of times, we have these confidence intervals. And then these are the ones that we'd want to select, the ones that don't intersect 0. Okay.
Sure.
And so you could, if you ran these fixed confidence intervals with a union bound, so a Bonferroni correction, then if you selected these, you're going to have some sample complexity that scales like if these gap were a very simple model, if it was either good or bad, either mean delta or mean 0, then the sample complexity for if you have n of these guys is going to be something n delta minus 2 log n. Okay, this is literally just setting this equal to this and solving for a number of trials. But this is very wasteful. It's not using adaptive technology in any ways. And can we remove this log n? Answer: yes. You can reuse LILUCB. It's great at adaptive sampling, as we just saw. Removes union bounds. But then your question: how do we actually select a set once we've taken measurements? Well, there's a one-to-one correspondence between confidence intervals and p-values. And given p-values, we can use Benjamini-Hodgberg to actually give back a set that's false discovery rate controlled, which allows us to grab a lot more of these guys without having to do Bonferroni correction. And I don't want to get bogged down too much in the technical details here, or even the algorithm, but the algorithm is very simple. It's basically you run LILUCB on the arms that are still in the running, that's still those confidence intervals that still overlap 0 essentially. And then at each time you run Benjamini-Hodgberg to select a set. You output that set. And what you can guarantee is that after some small number of measurements, no log n there, you can start to output a true positive rate controlled and FDR controlled set. This is optimal, true lower bounds. It works. It's a great actual algorithm. And so here's just some theory. I think this is a super cool result. It's very, very efficient. It works. But that's not the point of this talk. The point of this talk is, okay, so after I developed this algorithm for them, I was working with engineers at Optimizely, and I asked them to pull some data down. And so they obliged, which it was actually much harder than I expected. And this is a common thing. Whenever you go to a company, I just always assume that a company can easily pull down gobs and gobs of data to work with, and that engineers are always doing this. In practice, that's almost never the case. And it takes real engineering time to like write the Spark query or the SQL query to actually do this, and it takes a lot of computation to actually run that query, and it can take like weeks. Anyways, when they did that though, they got me some data, and I simulated it based on past data where they had lots and lots of experience, like A/B tests that ran for years, and we got 3x speed up. So it seemed to work on data that I pulled from the database, and they implemented it in the live work. But this was kind of deceiving because this is not actually what gets implemented. So many issues come up, and that's kind of what I want to focus on in the last 15 minutes or so. So these two experiences and additional experiences working with Kiva and Amazon really taught me a few rules that any adaptive experimentation on the web should really follow, or most adaptive experimentation. The first one being you have to support asynchronous interaction. You have to serve from a distributed or decentralized network. You have to be robust to time variation. And regret is almost always the wrong objective. And so I'm going to go through these one at a time, and hopefully it's not too laden with opinions. So what is asynchronous serving? So in both the REALML work, the caption contest, and the Optimizely work, or the A/B testing, it kind of assumes implicitly that Alice shows up. We ask her to take some action, rate some caption, and then send back a reward. And then after we receive that reward, then we send a caption to Bob. Bob returns a reward of whether it's unfunny or funny. And then Carol shows up and she returns her reward. In reality, people are showing up to the website one after the other, and they're not coming back with rewards. There's large delays in when people request a query and before they return the answer. And what this has the effect of doing is, if you're running an algorithm like UCB, this would be disastrous, because the state, you haven't received the reward yet. You haven't updated the means between Alice, Bob, and Carol. And so what you would do is you'd send the same exact query over and over until you updated, until you got the first reward back, and you'd update and send something else. There are fixes and little hacks, but none of them are particularly good to fix UCB, and really we have to go to a different algorithm. So any algorithm really has to deal with asynchronous. That's not what we talk a lot about in Bandit. So the web is a worldwide enterprise. And what can happen is, if you just have a single centralized algorithm located at one place, like Seattle, Washington, if you're trying to talk to Antarctica or Australia, the round trip time can actually take quite a while if you're serving something and coming back. And I really didn't appreciate this until I worked with Optimizely, where they spent so much time trying to optimize the size of the JavaScript snippet that they sent to customers on their websites. Because if they slowed down that website at all, they'd be dropped from the platform. And there's this great quote from an engineer at Amazon in 2006, saying what they did is they slowed down Amazon.com by 100 milliseconds, increments of 100 milliseconds, just to see what would happen. And what they found is that every 100 milliseconds delay that they added, they lost 1% of sales. And so this just goes to show you that, like, these delays that seem like it's not a big deal actually really are. And of course, the solution to this is just to decentralize. You have content distribution networks, locate servers all over the earth, and then so any request from South America is hitting the nearest server. Okay. Easy for serving static content. Way harder if you have an adaptive algorithm that has internal state that needs to be updated and serving. And so now you need to distribute this state to all these decentralized workers. And this can be an issue. And so basically, it amounts basically to the same solution as asynchronous serving. You need to have an algorithm that is somehow randomized and also doesn't need the state to be updated very frequently. The third issue is time variation. Humans are, not robots, and in reality, we'd love to have, someone shows up to the website, rates one caption, then leaves, because then that would maintain independence between the users. But in reality, they actually rate many captions at a time in a sitting. They might rate 100 captions in a sitting, because it happens really fast. And you can go and do this if you want. I think this link is still the right one. But we were getting kind of worried. Like I said, I worked a lot with psychologists at the time. And so we were very aware of primacy effects and things like this. And so we decided to, on a whim, do this experiment. We didn't expect much to come of it. And at the time, we had unfunny, somewhat funny, or funny in these captions. And we randomly showed these captions to people. Okay, so of the 5,000, we just randomly showed a caption at every single time. And so if people were Bernoulli sources, so if it was an individual person, and I was getting random captions, because they were uniformly at randomly shown, when I average over people, the probability of giving unfunny, somewhat funny, or funny, they should just be constant lines with respect to the number of captions that they've seen. But in reality, when we actually run this experiment, we see something that was unexpected at the time, but obvious in hindsight, that the unfunny, over time, you tend to dislike captions no matter what they are, right? So the more captions you rate, you're calibrating yourself, or you're just getting irritated and upset with the application, and you're deciding each one of these is less and less funny as time goes on. And like, this is a major issue actually, because if you have an algorithm that's optimistic, like Thompson sampling or UCV, this has the effect of the ones that are shown in the beginning, you're going to artificially give them a boost of a reward. You're going to say they're more funny because you just haven't seen many. But also because if you're using optimistic algorithm, you're far more likely to see a top rated caption so far than a badly rated caption so far. And so what this has the effect, if you're running any optimistic algorithm, you're basically is a rich get richer sort of situation. And you can have these runs where a caption isn't even that good, but can appear good in the beginning, and because of this effect, will stay good, and because just people aren't calibrated to it. And it's sort of a disastrous consequence. But for many years, I was just convinced that this is not actually a problem, because the core problem coming up here is that the same person's rating multiple captions one after the other. And so all this issue has to do with the fact that they're the same person. If we were to only look at the first, if we were to have the person rate one thing and then leave, this would not be an issue, is what I believe. And because this is the core assumption behind A/B testing on the internet. Someone shows up to the website, they either make it click or they don't click, or they make a purchase or they don't purchase, and then that's it. We don't track them more than once. It's just like every user is independent trial. And so at Optimizely, I tried to test this hypothesis because I just assumed it was true and I just wanted to verify that it was true. And so imagine you have 3 arms, let's say, 3 alternatives. And so at each time, you're going to, ignore this first line, you're going to assign some treatment of 1 to 3. Sorry, you'll see this language in a second, it'll make sense. The website's going to use that caption or use that alternative, that 1 to 3, and they're going to observe some reward, whether it was successful or not. And the model here of all A/B testing on the internet is that people from time to time are independent of each other, which is somewhat reasonable. And so there's some expected value of what the population believes, or how good sort of this variation is. And this is reasonable because you can say, well, humans or the visitors to the website are drawn from some distribution, and they're not all identically distributed, of course. Like, well, they're all drawn from a distribution, but they don't all behave the same. But I don't care about each individual, I care about the population. And so whatever rating, when I take the expectation over that population that's coming to the website, we should get a very good mean coming out of that and should be consistent over time. So this is sort of the model of A/B testing over time. You have some empirical mean that sort of converges to its true mean all over time. So when I had that engineer pull the data, though, I started looking at it, and I started to see a lot of data that looked like this, a lot of periodic data, where it would vary throughout the day, the time of day, on a 24-hour cycle, on a weekly cycle. People, and the reason for this is that people behave extremely differently in the morning before work or at work, and in the afternoon or evening when they're back home from work, where they might make the purchase. They might think about it or research during the day, make the purchase later at night. Or they might do a lot more, they might buy that airline flight on the weekend, but they might be tracking prices during the week. So behaviors are just extremely different as a function of time. There was also a lot of stuff like this where you get like weird periods where strange stuff happened. And this can happen when a microservice goes down on the website somewhere, and like it's down for a few hours and like weird stuff happens. Discrete shifts when the website has a sale, that's like the worst, throws everything off. And then the absolute worst one is the decay or RAM. These are really difficult to deal with, and it's not clear what even the right answer is, what you want to output. But to me, the only real solution here is to look at the running average. So this is, if you want to evaluate how good the ith alternative is, the only real metric that makes any sense at all is over some time period big T, which caption would have received the most reward if it was shown at each time T. Okay. Now, you don't get to observe what every caption or what every alternative would have done at time T. You only get to observe one. Because at time T, you only get to choose one, you only get to see one outcome. But we're smart. We know how to use inverse propensity scores, and we can get unbiased estimates of the reward of the alternative, even if we pulled some other IT, as long as the IT was drawn randomly from some distribution P2. And so this mu hat T, if you build this unbiased estimator, it's unbiased and we can control the variance. The variance goes down like this 1 over PT. And so then the issue just becomes, how do you choose PT? It can't go to 0. It has to be non-zero for everything. And so there's lots of, if you care about regret, there's lots of options, but they'll have pretty bad polynomial decay in the probability of error, necessarily, because they're low regret. And there's also other strategies like this P1 algorithm from Abasi et al. In 2018. This is an amazing, great paper that is not cited enough. I strongly encourage you to go to read it. It's probably one of the best A/B testing papers for the real world that no one reads or is even aware of. It's really quite amazing. It's a Colt 2018 paper. And then there's a heuristics that you can deal with. And so the final sort of lesson or final rule of mine is regret is rarely the objective. Okay. So suppose that Adidas has 3 landing pages that it could be showing. And the reward signal, like what are they measuring, conversion rate, or what are they trying to maximize? We're trying to figure out which variation leads to the biggest reward. Is probably money spent at checkout. And so what they really want to do, it seems like they want to figure out what if they're trying to figure out what caption is getting the most money, or what variation is the money, it seems very reasonable to say, well, actually, I want to play these ITs, these captions one at a time, or these variations one at a time, in order to maximize the cumulative reward at the end of the day. Because that's maximizing revenue. That's maximizing the amount of money this website's making. This should be like the only thing that matters. And I really believed this. Optimizing for the longest time, and I could not understand why anyone would run an A/B test. And of course, I was talking to the wrong people. I was talking to the engineers. And I didn't get it until I had lunch with a marketer, until I had lunch with someone that actually talks to the people that run these A/B testing experiments. And I was floored. Because you have to think about who is actually running the A/B test? These landing pages and these creative content are created by an artist, okay? They don't just come out of nowhere. So it's really important to understand what their interests are is they want to understand which one was the best. And they really want to be confident in that. Because there is not just running one A/B test. The outcome of this A/B test is going to inform what you do next, which is going to inform what you do next. So what they're really interested in is actually insights. They want to understand what is the properties of these that are actually making the difference. And so their goal really is pure exploration. And the more pessimistic view on this, and I'm not kidding, is very realistic, is that the person that's running the A/B test, they get promoted based on whether their A/B tests work or not, right? They don't, like, they're being paid to produce these content and try to get a lift. And so if they're doing regret minimization can have terrible statistical power. Sure, you could maximize reward over time, but when it comes to, can you determine that, like, does this actually do better than the control? Is this actually so much better than control? How much better? Regret minimization doesn't tell you that. It has a very bad polynomial decay in the probability of error, and it's just really a terrible algorithm for this. And so pure exploration really is the answer. And finally, so most experiments fail. Most experiments are bad. Some numbers are 10%, 20%, but only about 10 to 20% of changes or A/B tests actually result in changing something, actually finding a variation that works. And so there's almost always a trusted control. It's almost, you never want to deviate from. And so typically only a very small fraction, like 1 to 10% of the traffic, is going to be diverted to anything different than that control. Because they want the vast majority of traffic to enjoy the thing that we know works. And then if something's really bad in the alternatives or variations, we don't want most users to see those. And in this sort of regime, you're already going to get small regret because the vast majority of your customers are getting the good control. And so of that 1 to 10% traffic that you're diverting to do this A/B test with, you don't really care about regret about that. You want to figure out as fast as possible what is the best variation. And this has been true time and time again, even when it comes to robotics. People, even in something where, like, if you're making a mistake, that's costing money. But what you really want to do, what the engineers want to do, is they want to figure out what are the insights, what works, what doesn't work. We're always diverting a very small amount of traffic to new alternatives. And what we want to do is figure out what works and what doesn't as fast as possible. And so it really is a pure exploration game, even for contextual bandits in these sort of robotic applications. So I promised to end by 10:55, and we're at 10:56. So I don't have time to go through this robotics application, but it's very much the same thing, just from a contextual bandits perspective. But yeah, very exciting field right now. So I'll stop there and take some questions.
Yeah.
Thanks.
Thank you very much, Kevin. Amazing talk. So in case there are questions, just shoot them. You can just unmute yourself and ask aloud. I think we'll go a bit after 8, but I'll stop recording later, and you can ask some questions that perhaps you don't want to have on the recording as well.
Indeed.
So in meantime, I'm going to ask the first question. So one could argue that the objective of the company, which is on one part, they want to understand what could be the change which leads them to a larger revenue, but they also want to maximize the revenue. So could you not argue that actually their objective is much more complicated? They just need to formulate it in a more informed way and then just deploy a regret minimization algorithm?
Yes.
Because it seems like they
don't like complicated, though. It's this goes back to the education sort of caveat. Like, it's really hard to, when you deploy something, especially as a person like me, I'm just one guy coming from academia and saying like, this is what you guys should be doing. But when I say something, there's like a team of engineers that are putting real money and real time into deploying this and coding this up. Like, I'm embarrassed to say that no, I do not code in Scala. I don't know how to do that. I code up a Jupyter notebook, give it to them, and then they go and implement it in, because they're adult programmers, unlike myself. And so like, if you're telling people to allocate time to do something, it's gonna have to be simple and de-risked, and they want to have to really understand it. And if you get some experiments, like if you get back results from an A/B test or something, and it's like, I guess it worked, like that's not acceptable. Like it needs to be like what you really want after you do an experiment or go and collect a lot of data and spend a lot of engineering time. You want whatever comes back to be very clear. Like, yes, we understand exactly what happened, and either worked or it didn't work. And now based on this decision, we're going to go here. And an A/B test allows you to do that. Whereas you can build a flow chart of what you're going to do before you even get the results back. In regret minimization, it's kind of a tougher sell. It's like, yeah, the company does want to make a lot of money, but like, how does that change what we do next? Like, how does that influence our plans for next quarter? And that's a sort of thought that I didn't really take into account when thinking about regret minimization or pure exploration. A lot of times people want insights from running experiments. It's not, and then they do the bigger sort of business decisions based on that. They're not really looking to minimize regret a lot of the time, in my experience.
Yeah, I also have this experience. Yeah, thank you. So any other questions?
So if I understood that correctly, you're arguing that at least in practice, we should somehow decouple pure exploration from regret minimization in a sense.
Yeah, I mean, I think there are situations where regret minimization makes sense, where that actually is the goal. And people try to convince me that in pricing problems, where they're trying to price things the right way, and like you can't, because it's a game, whenever you're in a strategic game, it doesn't make sense to do pure exploration, because you're not trying to learn anything static. And like you really do have to adapt, and you have to sort of, you're trying to make as much money as possible against an adversary, you really do have to, or a strategic agent, you really have to be, you have no choice other than just do their online game and maximize reward and minimize regret. But in any situation in which the situation is static and you can learn something and then take those insights and use them in the future, it's almost always better to it's always a pure exploration game, because of this trust control thing. This is like, I guess this was like one of the bigger lessons that I learned in working with, I guess working more with Amazon, I guess, where like they're very risk averse. They don't want, they have something that's really good. Engineering, like these robot policies, for instance. Like when I got to Amazon, I was like, yeah, let's do contextual Bandit. There's so much great work on this. We can implement, Foster Rockland or Teaming the Monster, all these sort of things. And like, that's just a joke. Like they look like at me like I'm crazy, because they're like, no, we've had a team of engineers for years working on this. They all have PhDs in robotics and control theory. Like, and you're telling me you're gonna like do some actions based on pixels, like some pixels to actions? Like, absolutely not. Because like we don't know what it's gonna do. And so it really, like, what they wanted to do is they had a lot of policies, like they hand code these policies, and they're really good. They're really, really smart. But they have knobs. And what they want to figure out is how should we turn these knobs in order to move in the direction of the right policy? Because, and they're interested in this, not to converge the optimal policy, but because these robots are constantly changing. The situations in the warehouses are constantly changing. And they can use that insight if they know, oh, if we always approach from the top versus the side, that always leads to better outcomes. And so on future robots or future sort of situations, they learn that insight from past data and they can take it there. And they wouldn't have been able to learn that, at least directly, through our regret minimization. And so
super interesting.
Yeah.
Awesome.
Also, I think we have a question in the chat. Eamon, are you able to unmute yourself? If not, I can ask the question. I don't know if we have some issues with the muting today. Oh,
Hello, can you hear me?
yes.
yep, we can hear.
Yeah, good. Yeah, my question was about the synchronous issues, like the users coming in at different times and you cannot update your policy.
Yeah.
Like it doesn't really go in the sequential manner.
Yeah.
Like, how do you typically solve this issue?
Yeah, so there's a few ways. The easiest way is to have use randomization. So the way that Optimizely solves this problem is, for even a non-adaptive A/B test, is they will assign some probabilities of what probability to play each arm, and then they will, once they have those probabilities, they distribute them to all their context distribution networks. And then what they'll do is that, because it's those probabilities are sent from a local sort of close by to you, and then because they're sampling from that probability vector locally, it's doing about the same thing as they would do if they're coming from some global sort of some centralized location, because there's been a lot of work shown. I forget the paper. It was that quote recently in the last few years, where they showed that batching, if you use an algorithm like Thompson sampling, or you're sampling from some probabilities, you really do not need to update those probabilities very often. If you run some randomized algorithm where you always are allocating sort of probability vectors for how to sample arms from, and then you return the rewards back to the centralized server, could be a non-blocking call and be very fast. You don't need to wait for an ACK. If you do that, then you don't need to update these probabilities very quickly. So you simultaneously solve the decentralized serving problem, where you only update you send those are the responses, the rewards get sent directly back to the centralized database or server, and then that centralized server sends the probability vectors that it wants to serve to all the local guys, and then they sample from those. So this can be accomplished through an algorithm like Thompson sampling very naturally. Then in that case, you'll send back the means or the probability vectors themselves. It can also be handled by any sort of like successive elimination type approach as well. But the real answer is randomization.
Okay, thank you.
Perhaps we can stop the recording at this point and continue with other questions.
Yeah, let's do it.